So welcome guys. So we have Thomas and Binsbergen talking about generalized parser combinator library. Over to you.
Thank you very much. Thanks. Yeah, so I'll be talking about parsing, parser combinators, and specifically generalized parsing and how that fits in with a combinator approach. So I divided my talk in two halves, each half which is itself divided in two. In the first part, I'm going to just briefly introduce parsing as it is taught in an undergrad course, just to remind us and set up some terminology. Then in the third part, I'm going to mention some of the problems that arise with the basic recursive descent parsing that I'll introduce here. And in the second part, I'm going to discuss a very naive implementation of monadic combinators which are based on the recursive descent idea, just to give an idea of how these work and how you can use such a monadic parser combinator library. And specifically, I want to highlight some features that I think are very important in relation to other alternatives like parser generators that we may want to decide to use. So then I'll be talking about generalized parsing and see how generalized parsing solves some of the problems that arise from using the recursive descent strategy. And specifically I'm going to talk about the GLL, generalized parsing algorithm, which is a generalization of the recursive descent idea. And then I'll be talking about combinators which use generalized parsing as an underlying parsing technology, and specifically what kind of library we end up with and what features such a library has. So just to remind ourselves very quickly, I'll be talking about symbols, which come in two flavors. We have terminals and non-terminals, and we say that non-terminals are non-terminals because they expand into a sequence of other symbols. And we call, so the non-terminal has a number of productions, and a set of productions forms a grammar. So for example, there's a small grammar here which shows two productions for the non-terminal x, and we have this alpha and beta, which are sequences of symbols. So we say that x expands into a certain sequence of symbols, alpha. Then we can ask questions like, does x, non-terminal x, derive a certain input string of terminals, which is the same as asking, does x keep expanding until we end up with a string that is equal to I? So here's a small example of a grammar which just for basic arithmetic expressions. So we have a number of productions here. I've written the terminals on top. And now we can ask a question like, is there a full expansion of E0 into this string? If I were to answer this question with yes, which I should, then this is only recognition. So, but rather I would like to provide a proof of some sort that this is indeed the case. And we can provide a proof in the form of a parse tree. Or better, we can actually perform the kind of evaluation on the fly. So that in this case we would actually evaluate to the value 7 rather than producing a tree which represents this expression. So now I want to explain the basic idea of recursive descent parsing. So how so this is a strategy for finding such proofs. And the idea is that every symbol is implemented by a parse function, where a parse function receives an input string as an argument, and some kind of pivot. And I use the word pivot for an index into the input string, because the idea is that this index will represent how far we have matched into the input string so far. So the pivot splits the input string in two, in a part that we have matched and a part that we haven't matched yet. And the parse function returns a new pivot because possibly we have matched more terminals, and either a bit of a parse tree or a semantic value. I use the word semantic value for some result of computation like this for this evaluation that we may perform on the fly. Then for terminals, this is very simple. So the parse function for a terminal just matches a single terminal against what the current position in the input string. For a non-terminal, the parse function has to choose one of the productions for that non-terminal to execute somehow, and then it needs to execute all those symbols in that production in sequence. So this idea underlies basic parser combinators by using the following observation, that we can forget all about symbols and productions and we can just focus on the parse functions themselves. So we can introduce some combinators or operators to combine parse functions and so we have an operator for choice and sequence. So now I mentioned that we somehow choose a production, so I deliberately left this open, how we choose this production, because this is where a lot of problems come up. So now I want to switch to a bit of Haskell code for implementing a very naive basic combinator library. And here, so I've written three different types for representing these parse functions, and they each implement a different strategy for handling choice. They each represent a different choice strategy. In the first case, we say we just pick one alternative and stick with it. If this alternative doesn't lead to successful derivation, then we just give an error and stop. In the second case, we use a maybe type to represent that an alternative may fail. And so the idea is that we can choose an alternative, and if this fails, we can try the next alternative, and we can keep doing this until one alternative succeeds. Another option is to just try all alternatives, and whenever they give results, we accumulate these results to a list. So we use a list to represent the multiple results that we then may end up having. So going with this approach, I can So I've wrapped this type of parse functions in a new type so that I can give class instances later. And I define this function parse, which given some parser and an input string gives us the multiple semantic values that may end up from performing this parse. So we run our parser with some given string and the initial pivot of 0. And then we filter all our results, so we only take out the ones that have a pivot of m, where m is the length of the string. So we must match until we must match the string entirely. And then, so here's an example of a parser. So we use applicative style here, and I'm going to give the instance for applicative later. And the idea is that this is a parser for counting the number of consecutive A and B characters in a string of ABs. So we want to match an A, we want to match a B, and then we want to recurse. And alternatively, if there's nothing left to match, then we just succeed by returning this semantic value 0, indicating that we haven't matched any ABs. But because we increment whenever we match an A and a B, we increment the result of the recursive call, so that's how we are counting. So this is performing evaluation on the fly. All right. So this is the function term is a function that, given some kind of term, produces a parser for matching exactly that terminal. So it's very basic. If the terminal is in the current position in the input string, then we return the singleton list in which the pivot is increased and the pivot is paired with the terminal. Otherwise, we have failure, which is represented by the empty list. So now we can observe that such a parser is actually a functor by giving an fmap definition. So if we look at the type, and so I specialize the type here just for parsers, we can see that if we have some functions for transforming A's into B's, and we have a parser that produces A's, then we can produce a parser that produces B's. And we do that by running the parser on the same input string and the same pivot k, and whatever result we get, we just return that result, but now we have applied our transformer function to the result A. Yes? So of the type, I presume. The parser data type. Yeah. So this is the type, but the parser data type itself is just a wrapper around this type. Around which one? Parser 2. Yeah. Right, so yeah, something terrible has happened. I've been renaming these types. I should have been using the one parser 3 here actually. So I've updated the numbers here, but not in the rest of the code. It's a bit unfortunate. But yes, I am using the list version here. Sorry for that. So it's clear this way, I hope. Yeah, indeed. Yeah, apologies. Yeah. Further, we can observe that it's an applicative functor. So in the case of pure, we would have just a parser that always succeeds and returns the given A as a semantic value. So the pivot is not updated. And the star operator would perform sequencing for us. So the idea is that if we have a parser that produces functions from A to B, and we have a parser that produces A's, then we can return a parser that produces B's. So first we run P with the given pivot L, which is given here. Then we get a new pivot K and some function for transforming A's into B's. We use this new pivot when we run parser Q, and then we get our results, which we will just return, but only after having applied our transformer function. And I'm introducing succeed as a synonym for pure, just because the name is more suggestive of the parsing that we're doing. Then we can also observe that parsers can form alternatives of each other. So we can represent choice between parsers. So these parsers must produce values of the same type, otherwise they are not valid alternatives. And the idea is we just run both parsers and accumulate our results. We must also show represent failure somehow, which is what the empty method denotes. And failure is just returning the empty list. And then I'm introducing again a synonym here, fail, for empty. And then it gets more interesting when we observe that parsers also form a monad. So return is just pure. And bind becomes a special version of sequencing where we actually have a function for producing a parser which depends on the result of another parser that is given to us. So the idea is that we run the parser P on the pivot L. This gives us a semantic value A, and then we can construct a new parser from that A and run it, again using the new pivot K. So this is a maybe surprising result if you think from traditional parsing perspective, that we can construct a parser by using intermediate results. So our final parser, the actual structure of that parser depends on having run a parser somewhere halfway through in order to decide exactly how we are going to construct the parser here. So that implies some kind of context sensitivity. So I think this is this is a quite specific feature to parser combinators with using parser generated technology. That's definitely something we cannot achieve. Another such feature is defining basically alternatives for our term combinator. So remember, term is just a function that, given some kind of terminal, produces a parser that matches that terminal. But we are not limited to just matching terminals. We can do much more. For example, we can define a function pred, which returns a parser that matches all the terminals that satisfy that predicate. Similarly, we can write a function prefix, which returns a parser that matches all prefixes of the current position in the string. So we are given some string of terminals. If this string of terminals forms a prefix of the substring that we're currently looking at, then this parser succeeds. Now we can do this because the internals of our combinators are relatively easy. Our part functions are simple, sequencing and choice is simple, and given that we understand how these internals work, we can define such functions. And I think this is an important aspect as well. Another important feature of these parser combinators is defining derived combinators. So these are combinators that are defined in terms of already existing combinators. So we can basically extend our domain-specific language for writing parsers. So for example, wrapping a certain parser around with parentheses. So we want to execute some parser within parentheses, or within braces, or within brackets. And for this we use the derived combinator within. And of course parents and brackets and so on are derived from within. And then I'm defining some other functions here, some other parsers, which are going to help me in the more interesting example that I'm showing on the next slide. So first, I'm defining something that matches identifiers, where an identifier is just any lowercase character, something for natural numbers. and something for matching an arbitrary number of spaces, so matching any white space character. And using those functions, I'm going to define a parser for parsing array declarations. So just as an example of how this works, we have a string here which suggests to declare an integer array of size 3, and then we call it x, and then we give it 3 default values, which is accepted by our parser. But the following string is not accepted. It is not accepted because we declare an array of size 2, but we give it 3 default values. So here we see an example of this context sensitivity. The fact that we parsed 2 here influences what further part of the string we can match. So this parser is written as such. So now we use do notation. And so first we want to match some kind of keyword. So this is just a synonym for prefix. We want to parse the size of our array, which is a natural number between brackets. We match we want to obtain an identifier. We match an equals symbol, etc. And here the interesting part, we have some function thatMany, which matches a certain amount of natural numbers, comma separated, and which number it matches is determined by size. So briefly have a look at thatMany. So if the given natural number is smaller than 0, it will always fail. If it's 0, then it will always succeed, returning the empty list. If it's 1, it will execute the parser once and put the result in a singleton list. Otherwise, we run the parser. We also want to match a comma, and then we make a recursive call where the n is decreased. So far, this has been a bit of a good news show where everything seems to work nice and well. But as you are probably aware, something like writing a left recursive grammar will not work with the recursive descent approach. So over here, if we define an alternative which immediately recurses, so I'm defining an x per 0, which recurses immediately on x per 0 here. So if we choose this alternative, which we will choose because I'm choosing all alternatives, then this will the parse function for x per 0 will call itself without having updated any of its arguments, and it will of course not terminate. And yeah, so what kind of string actually you want to match that doesn't influence the result at all. We will always fail to terminate. And this is an example of a highly ambiguous grammar. It's a bit of a nonsensical example, but it shows that even a very small string of 25 characters can already take ages to compute. And when I say ages, it means that I'm not patient enough to wait for it to finish, which is not that long actually. So now I want to jump back to my slides, and I want to highlight this problem a bit more. So let's consider this node to be a function call to a specific pivot. So it's not a parse function for E0, it's a parse function applied to the pivot 0.
Can you just remind us what the pivot was, what its index was?
So it's an index into the input string.
And what does it mean?
So it means that how far we have matched into the string. So that's So it's the terminal at that index in the input string. That's the first terminal that we now want to match in the remainder of the parse.
So it's where a traditional parser would just keep the tail of the string, but you're keeping the whole string plus an index into where you're
Exactly.
interested.
Yeah. Exactly. Yeah. Right, so this is a parse function for some non-terminal E0 that it's going to have to choose between alternatives A1, A2, and A3. And as I mentioned, I discussed these 3 options, so we can either pick an alternative and stick with it, or we can backtrack to the first alternative that succeeds, or we can just try all of them, or execute all of them, and somehow accumulate the results. Now, if one of these alternates immediately requires a call to E0,0, so apply the parse function E0 to 0, then we get a loop in this diagram. Now, the other problem, so the previous problem that occurs for all of the 3 choices that all possible strategies for dealing with choices, the 3 different strategies I mentioned. So whether even if we pick just an alternative and stick with it, we may still end up picking the left recursive case. The other problem occurs whenever we take one of the other strategies where we apply backtracking. And so the problem is having to make this choice, which alternative to choose. And in a traditional compiler course, you're being told that we may transform our grammar, or the parsing technology may use look-ahead. So we do some pre-computation to determine for each alternative what kind of terminals it can start to match. But no matter how smart your parsing technology is, it will not be able to make the perfect choice anyway. So any algorithm that chooses to choose an alternative and stick with it without backtracking cannot be complete, in the sense that it will reject strings that are actually part of the language. Now, whether that's a practical problem, that's another matter. But this is where generalized parsing comes in. So the idea is that we want to be able to parse, to obtain a parser for an arbitrary context-free grammar. We want to explore all alternatives. We want to find all possible derivations, but still do this relatively efficiently. So there are a number of generalized parsing algorithms out there. Some of them are very old. So early parsing I particularly like. And there's GLR, so this is generalized bottom-up parsing. And so in these days, those parsing technologies are mostly used for natural language processing, where ambiguities are common, and that's actually the thing that we are interested in. So we want to parse a piece of text and find out where the ambiguities are. But more recently, people interested in programming languages have also started adopting generalized parsing because of this idea that you can come up with a very abstract grammar which represents the abstract syntax of your language very nicely. And you can already obtain a parser for it if you use generalized parsing. Now that raises another problem, because now we have all these different interpretations that we have to deal with, because the more abstract your grammar, the more ambiguous it's likely to be, and the more interpretations the parser will generate. And this issue of ambiguity is very much open still, and there's research going on there, and it's definitely unresolved. Particularly I want to highlight the GLL algorithm, which is relatively new. And so the idea is we explore all alternatives, but we make sure that no parse function is executed with the same arguments multiple times, so only executed once. And if we do this and we use efficient data structures, then we can implement this algorithm such that its worst case runtime is cubic, and also its space, worst case space is also cubic. And the idea is so it computes an efficient representation of all parse trees, and I'm saying specifically an efficient representation of all parse trees rather than all parse trees, because of course there could be actually infinitely many parse trees or exponentially many, and if we were to enumerate them all, then we would never have a cubic algorithm. So that's a bit of an interesting observation here. So what I want to discuss, I was thinking whether I should explain the GLL algorithm in detail or not, and I decided to explain what Johnson presented in his paper in 1995, which is a memoization strategy, which is actually very close to what the GLL algorithm is doing. So I want to explain this form of memoization, and I also want to explain the absolute minimum that we need to do in order to represent all parse trees. So Johnson's memoization, the first idea is that we use continuation parsing style. So where previously in our combinator definitions we just return a pivot, which is possibly updated. Now we have as an additional argument the continuation, which is just another parse function, which we will apply to our new pivot. So instead of returning, we will apply the continuation to our result. And then the idea of the memoization procedure is that not only will we remember results, so that's the classical memoization, that when we apply a function to the same arguments, if we already computed the results for those arguments, we can just, well, it's cached, we can look it up and return it. But now we will also store the continuations. And how is that being used? Well, I'm trying to demonstrate that with this picture here. So we've seen this before. So this is a parse function which is applied to a certain pivot, in this case 0. when it is called using a certain continuation C1, then we store this continuation in the memo table, so it's floating around here on the left. And then we're going to execute all alternatives. Now let's say that one of these alternatives produces a result R1. I don't care which one, but one of the alternatives produces R1. In that case, we also store R1 in the memo table. And we apply all the continuations that we have stored so far to our new result. So that ends up, so we end up applying C1 to R1. Now it could be that from some other parse function we'll now call this parse function again with pivot 0, but this time with continuation C2. In this case we'll store C2 in our memo table as well, and we won't execute the alternatives because we've already done them. So here we can recognize that this is a second call to this parse function. But also we need to apply the result that we already have. So this is the classical memoization step. Our previous result R1 to our new continuation C2, or the other way around, we apply C2 to R1. Now it could be that we receive a new result, say R2. Again, we store it in the memo table, and now we apply it to both C1 and C2. So we end up with these applications here. So the crucial idea is that all arriving continuations are applied to all arriving results. And this, at least intuitively, suggests that we are being complete. Everything that if we were exploring all alternatives, just as we did before with our naive combinators, using this approach, we still explore all these paths, but we avoid a lot of duplication. Because only the first application of this parse function to pivot 0 will actually execute the alternatives. And no continuation is applied to the same result twice. Now, I haven't explained how this is achieved, but this is a very crucial step here. So, how do we obtain information? Yes?
Can you come back a slide? Why did you not apply R1 to C2 when you came with the second pass?
I did here.
Oh.
Yeah, I put it on the left. Yeah, I put it on the left because the C2 was new,
yeah.
right? And so these are all triggered because of new results, and these are triggered because of new continuations. So if there was a new call with a continuation C3, then we would apply C3 to R1 and R2, and I would have put them over here on the left. Yeah.
Under which circumstances when you have R2, because you've already R1 and you minimize it, so when would you do R2?
Well, so first of all, one alternative can produce multiple results, but also we're executing multiple alternatives. So the absolute minimum of information that we need to somehow maintain in order to find all possible derivations, to represent all parse trees, is what I call extended pack nodes. And the idea is whenever we match a certain symbol, say E1, we must remember the production we are currently in while E1 was matched. And I'm representing this using this production notation where I put a dot behind the E1, suggesting that we have finished matching E1. We must remember the pivot at the time that we started matching the production. We must remember the pivot when we started matching the symbol. So in this example here, these two will coincide, because when we started matching the production, we also started matching E1. And we must remember the pivot after matching the symbol. And the intuition behind this is that think about running this generalized parsing algorithm, and we have basically a set of all these pack nodes. We have a lot of this information, which is sort of being printed out. You can think of this as a trace or something. And at the end, we can use this information to run the parse again. But now, whenever we have to make a choice, we know in which direction to go, because that's exactly what this is telling us. So we can make the right decision at every point. And this is an idea that has been used in the implementation of the library that I want to show in the end. So now I also want to discuss the bare minimum that we need to do in order to implement such an algorithm, like the Johnson memoization that I just shown, or GLL, as part of a combinator definition. And the crucial part is that GLL requires unique identifiers for symbols. We need this because we have this memo table, and we need to have keys to this table, and we wanted to avoid executing a certain continuation multiple times. So we also need to uniquely identify these continuations. So we need some kind of grammar information that the conventional parser combinators that I showed earlier does not provide us, because there the point was, let's forget about symbols, let's forget about productions, let's just focus on parse functions. So this is certain information that we don't have. So what is the absolute minimum information that we need? Well, my conclusion is that we need to identify recursive parse functions in order to avoid this left recursion problem. We also need to identify costly parse functions, where costly parse functions are the ones that you expect will be executed multiple times with the same arguments. So this is basically saying for these kind of functions we want to apply this minimization procedure that I explained. And from this I draw the conclusion that all we need is observable sharing. And this is a point where maybe some of you realize that this is a bit of a problem, a bit of a showstopper. Because observable sharing sort of conflicts with the idea of referential transparency. And but there is a very trivial, simple solution, in quotes, which is to ask the programmer to insert this information for us. So with the programmer I mean someone who's using the library and is writing parser or So the main problem is that we need some additional information that the conventional combinators do not provide us. And this is this statement is applicable to all the combinator libraries that exist nowadays that use some kind of generalized parsing technology under the hood. So I've listed a couple here. So eXchange has been developed in 2008, and I think it has been mostly used for language processing as well. And then there's some recent ones in OCaml P3 and Meerkat parsers, so these dates correspond to papers that have been published which describe these libraries. And then there's the GLL combinators that I want to talk about that I've been developing over the last years. And separately there's the grammar combinator library in Haskell, which doesn't actually provide generalized parsing, but it has this important idea of that we actually use combinators to describe a grammar rather than a parser. And that's an idea that I've adopted in my library as well, and the same applies to P3 and a lesser extent to the other libraries. But all these libraries must have some kind of choice of how to deal with, of how to obtain observable sharing. So this is a bit of a diagram to show the overview of the GLL combinators library. So on the bottom I've written a box for expression, and when I say expression I mean whatever it is that the programmer will write with the intention of obtaining a parser. And from this expression we can extract the grammar. And then using the grammar we can apply some external GLL parser or any other generalized parsing algorithm together with some input string. So this is this algorithm must be defined as an interpreter, which receives both the grammar and some input string as arguments. Then the parser gives us this derivation information, these extended peg nodes. Also from the expression, an evaluator is extracted, which is basically doing what I suggested earlier, is running the parse again, but this time being guided by the derivation information, so that we always make the right choices, and then apply the semantic actions which will give us the semantic values. Now, if we do this without any disambiguation, then we just end up with what we started with, which is all possible semantic values each corresponding to a particular derivation. So disambiguation is a bit of a black cloud which is hanging over this picture. And so there's a number of things I want to say here. So first of all, it's clear that the internals of this library are much more complicated than what I've showed earlier. And because of this complication, defining functions like pred and prefix, which provide some kind of alternative to just terminal matching, have become much more complicated, because this would require making some kind of change to our parser here, and we would have to change the grammar representation perhaps. So this is something that that maybe as a library designer you can do, but it's definitely something you cannot expect your users to do. And then there's the question of how to actually achieve disambiguation as part of such a library. So ideally you would have some kind of combinators or options that you can, some additional parameters or some kind of global option data type which represents, which contains disambiguation strategies. And ideally, these strategies would apply to the grammar. So you actually transform the grammar into a less ambiguous one, which would result in the parser running faster, etc. So everything downstream will benefit. But I don't think this is, at least in a more general, this will not work. Maybe for small examples this is possible, but definitely not a general solution. And then I want to distinguish between top-down and bottom-up disambiguation. And when I say top-down, I mean the disambiguation which takes place sort of on this arrow, where we, when we use the derivation information in the evaluator, we sort of prune our derivation information to contain less derivations. And so we have these pivots in there, right? So we have all these integers. And so something like longest match can be easily implemented as a disambiguation strategy, where if we have 2 pivots, we can just choose the larger one over the smaller one, for example. So I think this is a very feasible approach where we can sort of prune on the fly what the evaluator executes based on some information provided by the user. And if the disambiguation strategies are complete, then this would in the end result in a single derivation. Bottom-up disambiguation would be less desirable, but it would be more powerful. And the idea is that we will choose the multiple alternatives still, compute their semantic values, and then somehow, based on what these semantic values are, make a decision between them. But so that still means that we are computing a lot of semantic values that in the end we will throw away. Of course, if we have the semantic values, 2 semantic values, 1 for each alternative, then we can just apply any function that decides between them. So that's very powerful, but that will not lead to great efficiency improvements. Okay, so now I want to jump to showing how one uses the GLL Combinator library. So the package in which this is all implemented is called GLL. So it's just on Hackage and you can download it. It provides a separate GLL parser, which was the parser box on my picture, and then it provides gll.combinators.interface as a module, which, as the name suggests, forms an interface for this GLL parser. Now, so to finish the example that I started with, so this is again basic arithmetic expressions, but now written in a very abstract fashion where we don't use priorities or anything like this. We just write a completely recursive definition here. And the crucial difference is that we have this combinator here, which explicitly introduces a non-terminal. And this is where the programmer is asked to introduce some grammar information. So in this case, in the form of a string. So because we have the string here, we can use memoization, etc. Now, of course, because this grammar is highly ambiguous, so when we actually start parsing, we will get multiple semantic values here. So for this string, there are these possible interpretations. Now, as I mentioned, disambiguation is still pretty much an open problem, and I've just been experimenting with some kind of disambiguation strategies and how I would go about implementing them as part of this library. And well, something that is very simple is, so what I did is I provided a version of this combinator which makes it that each immediate child for the choice operator is now left biased. So we can use this to specify operator precedence. So now we group together plus and minus, and we group together multiplication and division because they have the same priority. But it's still, when we now execute this parser, that still doesn't fully disambiguate, because if we have, because we still can't decide between, in this case, 1 plus 4 minus 5, because we haven't taken associativity into account. So here I want to show another feature, which is so this is an example of a version of a combinator which somehow performs some kind of disambiguation. But it's also possible to provide options as parameters. So in this case, this is a global option which is applied to the entire combinator expression. And this is basically saying, this is applying longest match that I described. So this says whenever we have a choice, prefer the higher pivot. So that means that all our sequence combinators here now, so they form longest match, which has the effect that all our operators are now left associative. So when we run this parser, we get just a single result here. Now, I mentioned earlier when I showed the monadic parser combinators that they have certain features which are quite special that we would like to obtain in a combinator library like this. I already discussed these alternatives like predicate and prefix, which are not really feasible for users to define as for the users of this library. But also derived combinators, defining derived combinators is more involved. So derived combinators are combinators just defined in terms of already existing ones. So a typical example is what in the applicative libraries, the many function. So I've defined a version here, I'm calling it multiple. So we just want to apply a certain parser a number of times. And the issue here is that the function multiple receives a parser, or in this case a grammar expression, as an argument, and it needs to take this argument into account when we provide a non-terminal name here. Because if you just use the name of our function here, then what the kind of argument that to which we apply this function is not taken into account, which results in memoization firing too many times. So when multiple is applied to two different parsers, they will still share their results, which is of course not what we want. So the result here, so the solution is to somehow combine some kind of unique name for our function with a unique name obtained from our grammar expression. So this function make nt is doing. But the point I want to make here is that we now have to know a little bit of the internals of the library in order to define our derived combinators. We have to know which method of observable sharing is being used in order to define this. So in this case, I've just been using strings and asking the user for strings. But any other method would also have to be taken into account. Yes, and I think which I didn't mention is that because of this multiple phases approach, that we first extract the grammar, then extract the derivation information, and then perform a separate evaluator. Because of this approach, something like a monadic parser is definitely ruled out as well, because we have to first complete a parse to obtain this derivation information, then prune these results, and then execute our semantic actions.
Yeah, if I understand correctly, we're now pretty close to the original model of having you have a parser, some DNF syntax, and you make a parser. It's like a parser generator. You give
exactly,
it a bar,
yeah.
and it gives you back a bar. So it's almost the same approach, except that you can give some more information for memorization, which might not be possible.
Well, so you're making a very good point, which is a point I was hoping to make as well, that actually I think we should be comparing a library like this more to a parser generator than maybe the combinators that we saw earlier. So the question is, if you want to use a library like this, you have to weigh the benefits in comparison with a parser generator approach. And I think those features that I mentioned, like deriving these alternative elementary combinators and defining derived combinators, and maybe doing some kind of context-sensitive parsing, those are the features that are unique to parser combinators that a parser generator cannot offer. So I think people that implement libraries like this should take this into account. I already argued that these alternative elementary combinators are definitely very hard to define because the internals of the library are so complicated, but also these derived combinators provide a challenge. I think I'd like to conclude my talk with this. Thank you very much.
As you are already working in an applicative framework, can you not just have a function called memo or whatever that generates a name wherever you want something to be memoized?
Well, so I mentioned this paper by Johnson, which has this explicit MIMO combinator, which you apply to a certain parse function that you've built up using other combinators, and then this will generate actually a MIMO table for you. So this is so it generates a MIMO table, and the closure that is computed refers to that MIMO table. So that's an approach that can be taken, but that doesn't help us with defining a combinator like this. Well, we can still define multiple or many, but we need to know exactly at what point during the evaluation of this combinator that MIMO table is being created. So we need to take this solution for observable sharing into account.
So the point is here that you want this multiple function or parser to also be memoized.
Well, so you want it to be memoized because it's recursive. So in this case, I've defined it right recursively, but it could also be defined using left recursion, and in that case, it would definitely have to be memoized. But the issue is that if the MIMO table is being created so the MIMO table should be created as part of the application of multiple to our argument here, so that each argument receives its own MIMO table. So that's sort of the same issue here. If we just provide a string without taking the argument into account, then we are sharing too much results.
Right.
Well, we can discuss it later if you're not convinced.
So can you give us some practical advice? When should we use a library like this, a generalized parsing library?
Well,
compared to, for example, when should we reach for parsec, happy? Where does this fit in with those existing? What use cases, what niche does it cover?
Well, so I'm thinking that of all the libraries that I showed that currently do something with generalized parsing, it's fair to say that they are all in a prototype phase. So I wouldn't suggest using them for any serious application. You can think of this that so generalized parsing itself, generalized parsing applied to programming languages or to more general applications outside of natural language is relatively new. But especially the idea of using combinators to somehow access a generalized parsing algorithm, that's something that people have been working on in the last couple of years. So there's a lot of design space that needs to be explored, because all the different libraries that I showed, so these ones, internally they are all completely different, and there are many more options that can be explored. And I think
so. In that case, perhaps my question is: when should we think of reaching for generalized parsing? What sort of problem would we be facing?
Yeah. Well,
where we got, aha! What I really need is to get rid of parsec. It's not doing the right thing. Get rid of happy. It's not, or whatever. I need generalized parsing. What kind of situation would make us think that was the right solution?
Well, so for me, so I'm using this library as part of my PhD research, and for me it's very useful because I'm thinking from the perspective of an abstract syntax tree. So because I'm defining semantics for programming languages, and so I have some kind of grammar that's sort of forms the beginning of my perspective, and from that grammar I can immediately obtain a parser. So if you adopt the perspective from a semanticist, someone who works in programming language semantics, you may not actually want to worry too much about the concrete syntax of your program, or how to make this transition from a more concrete syntax to your abstract syntax. And generalized parsing, yeah, at least it gives you a parser straight away, but then you have other issues to worry about, which is how to disambiguate, and that's a big open question which extends beyond combinators, of course. And this is something where a lot of active research is going on, and so we have to wait a bit, first of all, to see what kind of disambiguation strategies are really successful, and then we have to think about how can we apply these strategies in a combinator library framework.
Is there any interaction with error messages? I mean, I'm not interested in how much work you've spent, but I'm interested in whether this approach in general makes it easier or harder to produce good error messages, or whether there's simply no relevance.
Well, So, because this is particularly GLL, because it uses is a generalization for recursive descent, it therefore you can really pinpoint in locations in the grammar where a certain mismatch occurred. So from that perspective, it's nice. We can see this is in the string where we currently are in the string, and this is where we currently are in the grammar, and that didn't match. But the problem is that since we are applying all alternatives, we have multiple such pairs, if you will. So we have multiple combinations of a pivot in the input string and a position in the grammar that didn't match. And then the question is, which of those errors do you report to the user? Well, if you were to provide all of them, that would be way too much. And so this is again disambiguation. This is again which interpretation did the user have in mind, so what to present. So yeah.
So just to get a handle on where GLL fits in, am I right in thinking that GLL is kind of the same idea as what you get with regular expression matching, but just taken to more expressive grammars? In the way with regular expressions, you have this. Can be an exponentially large number of matches, but you get polynomial matching algorithms.
Well, so I'm not very familiar with the idea of using regular expressions and then building more powerful parsers using them. I'm not familiar with that.
I just mean, is GLL similar to the way regular expression matching works, or is it totally unrelated?
Well, I wouldn't dare to say, because first of all, I don't really know the regular expression matching that you're talking about. But what is definitely the case is that there's a big similarity between. So I mentioned these different generalized parsing algorithms, and they all have a lot of common because they are solving the same problem. So at a very abstract level, they are very similar. So I would say the difference are in the details, which potentially lead to more efficient implementations.
So what happens to your array example?
To my array example?
What happens to your non-context-free array parsing algorithm that you showed, and that was beautiful halfway through the slides?
Yes, well, I wouldn't be able to define it using my or the GLL combinator library, because it requires some kind of context information.
Thank you.